Perfect. We are live. Assalamu alaikum, everyone. Welcome to our first online conference of AI Summit and its third edition. Today's session is very special as we will start with topic of neuromorphic computing and SpiNNaker2, a fascinating topic at the intersection of neuroscience and next generation computing. Our guest today is also very special, Mr. Wadjih Benchikh. So, Mr. Wadjih is currently a neuromorphic engineer at Spin Cloud Systems GmbH, a former research intern at Jülich Research Center in Germany, one of Europe's leading institutions in brain-inspired computing. His work focuses on advancing neuromorphic computing and artificial intelligence. Wadjih is the former leader of School of AI Algiers, which makes it even more special to have him with us today. So, Mr. Wadjih, once again, it is our pleasure to have you with us, and the stage is yours.
Hello, salam alaikum. I have nothing to add. يعطيك الصحة déjà presented more than enough. So maybe باش ما نطولش عليهم, we need to start the presentation and to go to what's important now. So yeah, today I'm gonna present just a quick introduction to everyone to introduce what's really neuromorphic computing and just give a simple example what we usually do in Spin Cloud, which working on a SpiNNaker2 chip. So yeah, I'll just give you a glimpse into a brain-inspired computing, and maybe a lot of you will be inspired of it. We'll maybe start working on this field. So yeah, first, what's really neuromorphic computing? Maybe just the idea of it is just we want to make things really close to how the brain actually works. So as everyone knows, like the brain is the most intelligent thing, the most intelligence, most developed intelligence we know at the moment. So there is nothing we can there is nothing we can actually inspire from except it. So neuromorphic computing first goal is just to get inspired by the brain and make something close to it and hope it works. Also, usually we use spikes, neurons, and synapses, which is some really known notions in neuroscience instead of traditional logic used in artificial neural network. And also, we also focused on a lot of things that actually the human brain have, like a lot of characteristics such as parallelism, low energy use, and also real-time processing, which make our solution even more interesting and scalable. So yeah, why do we actually need this neuromorphic computing? So traditional computer are really power hungry. So like let's say let's just check the last GPT models or any LLMs. It takes really a lot of energy to train them or even to run inference on them. So actually, the barrier or the bottleneck of the state of the art of the moment is nothing else except energy. So we are not just it's not possible to scale them up because we are running out of energy. We are using like cities yearly energy for just to train GPT or run inference of it. So we really need to pass this bottleneck, and one of the ways to do that is neuromorphic computing. Yeah, the brain uses around like 20 watts, which is used by your laptop just to run. Like your laptop uses more than that actually just to run Chrome. So we really need to really need to rethink what are we doing in artificial intelligence at the moment to make something interesting. And also, the brain, as known, solve problem efficiently, which is something that we are interested in, and in a lot of ways, like even like finding solution or other factors of efficiency. And yeah, as I told you already, that we always try to mimic how the brain work, and also want to reach at least the efficiency or just get close to how the biological brain work. And this is just a picture for illustrating how the brain actually work. And we already know, a lot of you actually know that each time like going from perceptron to multi-layer perceptron, we are just every time just implementing or simulating something that the neurons or the brain have. And we are just going to the next step with neuromorphic computing. So yeah, to sum up, like what's actually what we are actually focusing on neuromorphic computing, we can say we have like researchers are working on two sides, like the algorithmic side, which is just finding new way or implementing new algorithms that work like the human brain. That's simple example, or like the most famous one is spiking neural networks. And yeah, we just want to get inspired by neuroscience, not just deep neural network, and implement things on just implement new algorithms that are more bio-inspired. And actually, this is also used in to solve like optimizations problem and stuff like that. It's not always AI. So like it's really the term is really general. And from the hardware side, where we are always trying to surpass the one human architecture and like the every bottleneck that our laptop actually have. So like we know that the memory takes so long we need a lot of time to copy the memory from to copy data from memory to computation units in order to do calculation and stuff. So yeah, we are always trying to make our hardware close to the human brain in a lot of factors in order to also this also will kind of get us to a point where we want to make the hardware and algorithm works together, because like if you have a really bio-inspired algorithm, sometimes it's not good, it's not easy, or it's not efficient to run it on your laptop or GPU or whatever. So it's always it push you more to kind of create or make a new hardware that can map or run your bio-inspired hardware, bio-inspired algorithms. And the factors that we usually focus on while building our hardwares or designing our hardware is one thing is to be analog. The second thing is local memory. For local memory, just maybe it's like the one human architecture bottleneck, because like we have the memory in different places as the computing unit, so we always have a bus to copy data from and to the computation unit, and it's just literally the bottleneck that don't let us go faster. Also asynchronous, which the majority of hardwares right now are synchronous, that they use the same clock, and the like neurons in the brain are totally independent of each other. So it's really good to surpass this and go further in hardware. And parallelism, which is a really important characteristic in HPC now. So yeah, let's maybe sum up what's the difference between traditional and neuromorphic. Use clock, the traditional use clocks, which is mean synchronous, use usually a global clock for all the components of the architecture, which make them not independent. Literally, we can do stuff with algorithms to make them looks like asynchronous, but the idea of neuromorphic is to make it event driven. So like if we have spikes or we have events, we run the thing. Otherwise, it's like it's not consuming energy, which make it more energy efficient and also make it more let's say um, closer to the human brain. Traditional hardwares usually has the centralized memory, means that we have a memory and the computation unit, and every time you copy things to the computation unit registers and do your calculation and copy it back to the memory, and always we are limited by the bus speed or bandwidth. And the idea of neuromorphic is to kind of have some distributed memory, and usually we call it in-memory computation, where we have a lot of small CPUs or like small computation units, and each one has a really fast memory, and they kind of work together in order to use only the data that we have locally in order to make things distributed and or let's say local or let's say we use the local memory. Also, traditional is sequential or sometimes parallel. This let's say this characteristic is already been treated by the GPU really good, so we are not really facing any problems in parallelism or anything. And also in terms of energy, usually traditional GPUs use it's really power hungry and use a lot of energy, but For neuromorphic hardwares that exist at the moment, they run on low power, like you don't like at least like less 100 times less than GPUs. And maybe just to give an idea of the algorithmic side, let's just introduce or give a brief like a definition of what spike and neural network. They are just normal, like artificial neural network, but they are just more realistic. Instead of using values like floating point values of the activation, we kind of push it to mimic the human brain or mimic the human spikes and communicate with human neurons, I mean, sorry, and communicate with spikes. So as you can see in this example, the inputs are spikes, and we have some neurodynamics that are already inspired by the human brain. And in the end, we'll just get a spike in output, which is quite good in order to solve some problems. So yeah, neurons send spikes, communicate with spikes, and also one of the most important aspects that spike neural network has is that it's time dependent, or it uses the time patterns. So, and also this is also a step forward, going closer to the human brain. So instead of just using values and get an output in one time step, we kind of divide the data between different time steps in order to make the network understand this time pattern and be more close to how the brain actually works. Sorry, I'm telling this how the brain will actually work, but this is actually what's neuromorphic is. So this is my goal to reach, is that we always trying to make a human brain or simulation to the human brain. So yeah, it's closer to the biology, but actually this SNS has a lot of problems that they are actually now not that efficient. We didn't at all could we couldn't at all close the gap between the deep neural network or like artificial neural network and SNN. So because of a lot of problem, the most important one is it's harder to train because we are using spikes and it's not at all continuous in the moment. So we kind of need to use some tricks to train it, like approximation and stuff. So it's one of the challenges now. Also, since we're talking about the training, let's say also the ways that we are training our deep neural network, for example, using backpropagation through time, is not at all biologically plausible, which means it's not at all close how the brain actually learn, because we don't really wait until we finish everything and then just do backpropagation to give feedback to our neurons. It's kind of our neurons are updating their weights and their activities um, independently or like locally. So there's a lot of there's a lot of research on this side of let's say bio-inspired learning rules or something like that. And also, yeah, it's actually a great task for the moment for robotics and sensors and vision, since it's also more energy efficient. So it's good to like we can just map it and like or put it on small devices that don't need cooling, don't use a lot of energy, and if it's run good, if the accuracy is good, it's really a perfect solution for this kind of applications. And for the hardware example, maybe we just can talk a bit about SpiNNaker2, which what I work on SpinCloud. We kind of apply let's say we apply neuromorphic solutions on SpiNNaker2 to like have a real application. So yeah, what's SpiNNaker2 chip actually? As you can see here in this graph, it's one chip is made of 152 processing element, which is a core. We call it usually a core, and this core is made like this. It contain an ARM Cortex M4, which is not a new ARM CPU, but it's actually good and energy efficient for the moment. And we have a local high bandwidth memory. This is what we usually call the local memory, 128 kilobytes. Maybe it's also, you are also wondering why the memory like is so low. And it's actually one of the problems in this kind of hardware, because like we are kind of used to see memories in gigabytes and stuff like that, but kind of in this field, we kind of have small, fast memories everywhere, and also we have a bigger one that you can use to store other non-important data. So yeah, we have this ARM Cortex M4, we have the SRAM, and also we have some accelerator that can do the instruction, some specific instruction really efficient. Like for example, we have the exponential, logarithmic, and a random accelerator. Also, we have some connections, SpiNNaker router, and also some links that we use to communicate between chips. And also we have DRAM, which LPDDR4, which is the 2 gigabytes DRAM that we like. It's kind of when you are coding your application, you just think of, you have this small SRAM to use it for, let's say, example, spikes. And then if you have a bigger data, for example, records or anything that you don't need in the moment while doing the simulation, you can just store it there and like load it later. So always you have the trade-off memory, like the two different memory, which kind of create an hierarchical memory system. And yeah, the good thing about SpiNNaker2 at the moment is that scalable. That like we have the chip, and like you can just have a lot of chips and connect them together, and you will have a really big system. And also it's event based, so it's like asynchronous. So like it's small core, like we have this 152. Its small core is literally working independently from each other, and they are just, we have some communication algorithms to communicate spikes between each other and stuff, but they are totally independent. And also it's neuromorphic because we have the three features. Actually, we don't only have the fourth feature, which is analog computing, because actually for example, if we go, for example, Wadjih, it has some components where they do analog computing, or like brain scale too. They just use CMOS and then do some um, they like have some component where they use analog actually. But for us, everything is digital. It's not as it's not similar to how the brain works, but actually it's a kind of good feature because it makes everything easy to implement here. Like we don't have any bottlenecks for the moment for your implementation. Maybe the only bottleneck that it's hard to implement, but you have all the tools to do all the tricks you want with it. And also, it's a cool thing that it's not on. It doesn't only work with the with SNN, but you can also run some deep neural network stuff in it. And actually, there's a lot of project that we are working on that use, like for example, normal computer vision models, map it on chip and stuff like that. So it's a cool neuromorphic chip that it can also run deep neural network applications. What we have actually now, I mean the hardware. We have this Spin Cloud board, which has 48 SpiNNaker2 chips. So each one is a small chip with uh, 152 core. Each core has 2 each chip has 2 gigabyte RAM. And this one is actually like, let's say for development, this one is in a really immature version now. Like we can run some application in it, but we are trying to have a good software stack to run it efficiently. And the biggest machine we have now is we have this in TU Dresden, 5 million core machine. Actually, it's not 100% filled yet. We are like, I think we are 80%. As you can see, some of them are still empty. But the cool thing that it's kind of one of the biggest neuromorphic hardwares exist right now. And if when I say 5 million core, it doesn't mean 5 million neurons, but literally each core can have like, it can load 100 of neurons or even more than that. So yeah, it's really cool that it's scalable and you can just connect them and run whatever simulation you have in mind. And yeah, maybe just to talk about the availability, because maybe a lot of you are interested into running things on SpiNNaker. on SpiNNaker2. So the actual availability now, it's actually now not available for remote access. So like we kind of just send chips, boards to institutes and stuff to do the research, but actually it's planned to create like a remote access to it, similar to like what we have for GPUs and stuff. So they can just have like get it SSH, join the SSH server and run whatever you have in mind, or like Jupyter Notebook stuff, Jupyter Hub. So yeah, maybe it's maybe until the end of the year or even before that, you can have access to the SpiNNaker2 workstation. Yeah, maybe just to give you an overview of how we do the software stack. What I mean by the software stack is just the way to run your things for SpiNNaker2, because it's the most challenging thing actually for neuromorphic chips. For example, if we go to Luihi, you need literally to run instructions, something really similar or close to how assembly do. So like for Luihi 2, you just need to do this instructions, and it's kind of one of the problems that keeping the field to develop, which is it's really a hard thing to implement things on this software on this hardware. So as in Spin Cloud, we're trying to make it easy for everyone to run things on chip. So we are kind of building the software stack. A lot of things actually exist for the moment, but yeah, we are making it even better and easier and make it easy for everyone to run things without any problem. So we have usually three applications. We have a Spike and Neural Network, where it's actually available now for certain neurons, where you just write your code in Python. We have a library called PySpiNNaker2, and you literally write your code in Python, and it will simulate everything on chip in a direct way. And also, it also accepts the NAR representation, which is neuromorphic interface representation. I think it means something like that. So like it's just a global way to represent your network, and you can just pass the NAR file to this chip, and it will map everything on efficiently on chip and run your application. But sometimes it's hard when you have a specific neuron in mind that is not default, or it's not a leaky integrate on fire or something like that. So sometimes it's a bit tricky that you need to go a bit down and work your stuff there. I mean, implement things in C or C++. But yeah, let's hope like until let's hope in the as soon as possible we'll be able to customize our neural dynamics and make it easy to implement whatever we have in mind. Also, we have deep learning, which is we have just like, let's say, different layers that we know in deep neural network, and you can literally just map it to the chip. And actually, we are every time trying to make the software stack mature for deep neural network. And actually, there's a team that's really working hard on this part. And there's generic compute, which is sometimes you have a really complex problem, or like the complex problem can be solved easily. Sorry, can be solved by this ways. But sometimes you kind of want to make it more efficient because you have an idea to optimize stuff. So you need to go to this level, which is literally in C, and you need to like write your code for each core and connect them together and stuff like that. So it's like more data flow graphs and event-based computing. So like you can literally control everything there, but it's a bit hard to implement things that you have in mind. And everything will just go to this common interface and communicate with the chip. And actually, this run like we have also one of the interesting thing that the chip don't have an OS, like what's called like mm, something like Linux or something like that. Like it's literally just a chip that run your simulation, and we have an experiment runner that kind of control this thing and map things on different core and different computation unit to make it run. So it's really lightweight and energy efficient. To wrap up what we've been talking, like maybe the talk, like the presentation is not that far, but the idea of it was just to give you an overview of the field actually, and just maybe motivate you to discover more the field. And to get the first step there, just have a global idea. Maybe I just went a bit in details in SpiNNaker2, just to have, because like when you talk in general about the hardware, you usually don't have an idea how it's really done, because we are just kind of used just to GPUs. So it was just a really good, nice idea to. I thought that it's a nice idea to just show you how actually the hardware or the architectures are doing in the moment. So maybe a lot of you will be also interested into doing research in the hardware side, not only the algorithmic side. So yeah, let's say the most important point that we already talked in the talk or on the presentation. Neuromorphic computing is literally just making and getting inspired by the human brain and applied and simulated on hardware. The field is a bit young, but let's say it's promising, especially with the energy bottleneck that we have right now. So let's say it's the third generation of AI, but it's still young. We don't have good results yet, but yeah, it's a really good thing to start digging into and doing research into. Yeah, and also the maybe the annoying thing that it requires both algorithms and hardware, and sometimes you really need to work with the two of them, because sometimes you have the right algorithm, but we don't have the right hardware for that. So you need to kind of do the two things together in order to have an optimal solution. Similar to what happened actually to GPU, where actually just the attention is a really good match for the GPU, which made the GPU win the hardware lottery. So let's hope we will have something in the close future that we kind of a certain hardware will win this lottery, and we can easily run this sparse neuromorphic application there. SpiNNaker2 is a major step toward making neuromorphic hardware practical. And yeah, our goal is just to make it easy to implement anything you have in mind, actually. And also, the good thing that it's not that complex, or we don't have a lot of restrictions to run things on SpiNNaker2. So anything you have in mind, you can do it there, and it will be 100 times more energy efficient than GPU. It will be real time, and also you have all the let's say human brain characteristic, except analog, of course. Maybe a lot of you have questions, so thank you for the talk. We have a long time for questions. If anyone is interested or have any question, I'm happy to answer here.
Okay, thank you very much, Mr. Wadjih, for this very enlightening talk, as it opens our mind into a new field in the AI field. A question comes from Kamal Brothen. Can you give some examples of actual applications models that were run and experimented on SpiNNaker2?
Mm-hmm. So yeah, maybe just a simple thing that anyone can already try, that just a normal LAF neuron. It's already implemented there, and you can just do any application that you can do with an LAF, like any classification, like anamnest or anything. But kind of for the moment, at least what I'm actually working on is more into solving optimizations problem in a neuromorphic way. So like, I don't know if you know max cut problem. It's just you have a graph and you kind of want to find the best cut in it, and a lot of ideas is to use like simulated annealing, or like the obvious like the traditional way to solve that. But in the literature, a lot of ideas actually exist for neuromorphic in the neuromorphic field. So yeah, we have like some applications of this max cut. We have random walk also on chip. So yeah, we are more focusing on this optimizations problem for the moment. But yeah, any obvious neurodynamic is already implemented on chip, and you can straightforward apply it and run it.
Yeah, thank you. Um, So the second question comes from me. It says, could SNNs with the hardware implementations of SpiNNaker2 or future like implementations in hardware eventually replace ANNs in specific use cases like edge AI or real-time sensing, given like the constraints of power consumption for sure and the accuracy?
Yeah, so for the accuracy, I don't like SNN is not that accurate for the moment. But let's say we are still searching for a way to train them because we still using backpropagation through time, the one we usually use for recurrent neural networks. So for the moment, SNN is not the best in terms of accuracy, but it gives another it has another, let's say, pros, that it's more energy efficient and also easy to implement on this, easy to run on this kind of edge AI devices. So yeah, also one the most interesting case is using event-based camera. So event-based camera is just imagine that you have a camera that don't take a video but just calculate the difference between two frames. And this application, this input is actually literally spikes. So like you have literally the difference in each second. So you can always feed it directly to the SNN, and it's usually more accurate than the normal NNNs.
Thank you for the answer. The third question comes also from Kamal. Well, how this computation scheme compares or competes with quantum computing?
I think quantum computing is far ahead because it's like you cannot compare it at all. We are still in the low. So it's not comparable at all. We are just trying to mimic the human brain. We are not trying to make like things really fast and solve NP problems, and really like we are not, the acceleration is not at all close to any quantum computing, any quantum computers. We are just trying to make it close to the human brain so we can find, let's say, more interesting AI solutions. So similar to attention, it was really good. It's a really good solution. Maybe it's not really inspired from the human brain, but we are just going from the side that maybe the idea to follow the human brain will just will give us some more accurate networks and really cool ideas.
Yeah. Um, so the next question also comes from me. So as you have said, SNS may be great at at temporal data such as like camera or EEG, for instance, data. But as you have said already, they may lack accuracy in certain tasks. So are there like approaches that combine the best of two worlds, like SNNs when it comes to encoding temporal data, and when it comes to energy consumption, and ANNs when it comes to accuracy, as if like
Mhm.
SNNs are like the like encoded data or gives a new form of data that will be passed to ANNs.
So actually, there is an idea that's called shadow learning, where you kind of train things on NNs and then kind of project it to SNN to make the inference more energy efficient. And it's kind of when you do this brute shadow learning, you kind of don't use this temporal pattern, but there is an idea that you can kind of start doing training with NN and finish it with spike neural network, because always the problem right now, we need a really good way to train SNN. We don't have it. We are just using backpropagation through time, which is far from the human brain. We have actually some local learning rules, but they are not as good as they are not good yet. So yeah, the problem with SNN is training. So this is one of the ways that we are using for the moment to surpass this barrier.
Yeah. Thank you very much. Uh, One more question from Kamal again. As a researcher working in neuromorphic computing, how much did you get into neuroscience?
Yeah, that's a really important question. Actually, in labs, usually our teams, research teams, we have neuroscience guys, like we are computer scientists and we have physicists and neuroscientists. So, and also, let's say you need to understand how it's actually working there, because sometimes the project is just to implement this idea that exists actually on the human brain. So, like, you just sometimes go to the neuroscientist and say, explain to me how this grid cells work. And you will get the idea there, and you will find your work kind of is fill the gap between the two, find a mathematical, let's say, representation to what's happening in the human brain and implement it on the on this chips or like on normal like simulated or whatever. So yeah, the idea as a neuromorphic computing engineer, you need to fill the gap between the two. You need to communicate or have some knowledge in neuroscience and have the skills to in maths and computer science in order to simulate these ideas that we already know there. And also maybe also a good point to talk about is that as a neuromorphic computing, when you are doing like as a neuromorphic engineer, you kind of also help neuroscientists to understand how the brain is actually working. So it's also a good point that we do sometimes.
Yeah. Thank you. So I guess one more question and we wrap up.
Mm-hmm.
Yeah, and yeah, question from Kamal also. The awaited question: do you have some resources for people willing to get into this field?
Mm-hmm. So maybe one of the best things to check is let's say a series of workshop or talks about spiking neural network. It's called SNUFA, snoofa.net. I'm sending it here in private chat. You can, I don't know if you can share it, but there's actually a lot of talks on topics like the idea of the snoofa. Just they invite people that made some really good papers in SNN, and they talk about their work. So it will just inspire you and like kind of help you go into the field. And yeah, maybe you just need to start about understand spike neural network, understanding spike neural network, and I think everything will just come after that. It's the door to enter the neuromorphic field.
Yeah. So with that, we finish our great meeting. Thank you very much once again, Mr. Wadjih. It was our pleasure, a great, great pleasure. We learned a lot in this meeting, and personally, I'm excited to learn more about this field, especially the intersection between the hardware and the software. It may be challenging, like to implement those algorithms mathematically into a hardware where we don't have laws, like you said. But yeah, it seems very like challenging and hopefully rewarding in the future. Thank you
Yeah,
once
yeah.
again.
Yeah, maybe just to finish, as if anyone have any questions later, you can just contact me on LinkedIn or whatever, wherever you can find me. So I'm happy to answer all your questions.
Thank you. Okay. Okay, thank you everyone for attending today's today's online conference, and see you tomorrow, inshallah, for another exciting topic, which is machine learning. Okay, see you tomorrow.
Assalamu alaikum.